Here's another Hess's law problem, similar in nature to the last one, but this one's a little more complicated. Our overall equation is given at the bottom: 2N2 on the left side, 5O2 on the left side, and 2-dinitrogen pentoxide on the right side. Alright, let's start by looking for dinitrogen pentoxide. It only appears in the second step of the mechanism. It's on the opposite side, and the coefficient in the mechanism needs to be doubled. Based on that, let's take the second equation and do not one but two operations on it. We're going to flip it around and double all the coefficients. Next, let's look for the nitrogen molecule. In the overall equation, it's got a coefficient 2 and it's on the left side. The only place where nitrogen is found in the steps of the mechanism is in the bottom step. It's on the correct side, the left side, but its coefficient is 1/2. Well, let's take that last reaction and quadruple the coefficients and the value of delta H. After we flip and double the second step, the coefficient in front of HNO3 will be a 4, and that will cross out with the 4 that we'll receive from quadrupling the bottom reaction. The liquid water, after flipping and doubling, will appear on the right side of the equation with a coefficient 2. The only other place liquid water appears is in step 1 of the mechanism, and liquid water does not appear in the overall equation. That means that we have to make sure that liquid water crosses out in the mechanism. Well, if liquid water is going to be flipped and doubled, that means it's going to end up on the right side with a coefficient of 2. And to cancel it out, we've got to flip this water and double it so that it ends up on the left side with a coefficient of 2. For that reason, let's take the first equation and treat it the same way that we treat the second equation, flipping and doubling. Let's rewrite each of the reactions after doing what we had listed: flipping and doubling, and quadrupling each of them. If delta H, if you flip and double a reaction, that means the sign of delta H needs to be flipped around. So if it was negative, make it positive, and double the magnitude. So a negative 285.6 becomes a positive 571.6. I'm sorry, this is negative 285.8 becomes a positive 571.6. For the second equation, the value of delta H is also flipped and doubled, so it's made positive, and double the magnitude of a negative 76.6 is a 153.2. Lastly, we're going to quadruple the coefficients in the third equation. We will also quadruple the value of delta H, but don't flip the sign because you didn't flip the reaction around. Now we have 3 steps in a mechanism. Let's add them all together and see what crosses out. The 4HNO3 found on opposite sides of the equation, those cross out. The two hydrogen molecules on opposite sides of the equation also cross out. The two liquid waters on opposite sides of the equation also cross out. The oxygen's interesting. In step 1 of the mechanism, it has a coefficient of 1 and it's on the right side of the equation. In the third step of the mechanism, it has a coefficient of 6 and it's on the left side of the equation. The one molecule on the right side of the equation drops the coefficient on the left side of the equation from a 6 to a 5. It's as if you're subtracting one molecule of oxygen from both sides of the equation. That gets rid of the oxygen on the right side, and it reduces the coefficient by 1 on the left side. After crossing out what we've crossed out, let's rewrite the overall equation. Hopefully it will match what they have listed up here, and it does. So we've reproduced the overall equation. That means we've done this correctly. The last step is to add the values of delta H, just directly as written. Add them up, and we get an overall delta H of 28.4 kilojoules, and that's your final answer.